Ever wondered what would happen if you fell into a black hole? Most people imagine being crushed or instantly vaporized. The truth is much stranger. It's a journey into the most extreme environments in the universe. Fasten your seatbelts and let's explore. Black holes are regions in space where gravity is incredibly strong. Imagine a star much bigger than our sun squeezed into a tiny space. That's the density of a black hole. Nothing, not even light, can escape their pull. Think of throwing a ball in the air. On Earth, gravity pulls it back down. Throw it hard enough and it can break free. With a black hole, the escape velocity is faster than light, and nothing is faster than light. As you approach a black hole, you'll encounter the event horizon. Imagine a boundary in space. Once you cross it, there's no going back. Gravity's pull becomes inescapable. It's like falling over a waterfall. Once you're over the edge, there's no turning back. Even though it's a point of no return, it wouldn't look like anything special. No giant sign or flashing lights, just blackness. This is because the light itself is trapped inside the event horizon. Get ready for spaghettification. As you fall deeper, gravity's pull increases dramatically. Your feet closer to the black hole experience a much stronger pull than your head. This difference stretches your body like spaghetti. Sounds painful, right? Imagine a pizza dough being tossed and spun in the air. The dough stretches outward as it spins. Spaghettification is similar, but instead of spinning, it's the intense gravity pulling you apart. At the center of a black hole lies the singularity. This is a point where the gravitational pull is so intense that not even light can escape. The singularity is shrouded in mystery, hidden behind the event horizon, the boundary beyond which nothing can return. It's a place where the known laws of physics are pushed to their limits and beyond. Imagine all the matter of the black hole squeezed into a single point, infinitely dense. This process begins with the death of a massive star. As the star collapses under its own gravity, it compresses into an incredibly small space, creating a black hole. The core becomes so dense that it warps the fabric of space-time around it. This is where our understanding of physics breaks down. The singularity defies our current theories, including Einstein's theory of general relativity. In this realm, the curvature of space-time becomes infinite, and the known laws of physics cease to function as we understand them. It's like trying to divide by zero on a calculator. The answer is undefined. Our mathematical models fail to describe the conditions at the singularity. This has led scientists to search for a unified theory that can reconcile general relativity with quantum mechanics. We don't know what happens at the singularity. It could be a gateway to another universe, or perhaps a point where time itself comes to an end. The true nature of the singularity remains one of the greatest enigmas in modern science. Does our understanding of space and time still apply? Near the singularity, space and time are stretched and distorted to unimaginable degrees. The closer you get, the more extreme these effects become, leading to phenomena that challenge our very perception of reality. Do the laws of physics cease to exist? The singularity forces us to question the fundamental principles that govern our universe. It suggests that there are aspects of the cosmos that we have yet to comprehend, and that our current theories are incomplete. It remains one of the biggest unsolved mysteries in science. As we continue to explore the universe, the singularity at the center of a black hole stands as a reminder of the limits of our knowledge, and the vast potential for discovery that lies ahead. Scientists around the world are working tirelessly to unlock these secrets, hoping to one day understand the true nature of the singularity and what it means for our understanding of the universe. Section 6. Time warps. Time behaves strangely near a black hole. Imagine a clock falling towards the event horizon. From a safe distance, you'd see the clock tick slower and slower, eventually appearing to stop at the event horizon. It's as if time itself is being stretched or dilated by the intense gravity. This effect, called time dilation, is predicted by Einstein's theory of relativity. It means that time is not absolute but is relative to the observer's frame of reference. Section 7. A different view. Now imagine yourself falling into the immense gravitational pull of a black hole. The very thought might send shivers down your spine. But let's delve deeper into this fascinating scenario. From your perspective, time would seem to flow normally. You'd glance at your clock and see the seconds ticking away just as they always have. The familiar rhythm of time would be your constant companion. You wouldn't notice your clock ticking slower or feel yourself being stretched. The environment inside your spaceship would feel as ordinary as ever, with no immediate signs of the extraordinary journey you're on. This is because you're falling freely along with the flow of space-time. In this free-fall state, the forces that would normally act upon you are balanced out, creating a sensation of weightlessness. It's like being on a very fast-moving train. When you're seated inside, you don't feel the speed. The train glides smoothly on its tracks, and you might even forget how fast you're traveling. You don't feel the speed, but someone standing on the platform sees you whizzing by. To an outside observer, your journey is a blur of motion, a testament to the incredible velocity at which you're moving. Similarly, someone observing you falling into a black hole sees time slow down for you, but you wouldn't feel any different. To them, your descent appears to decelerate, as if you're moving in slow motion. This phenomenon, known as time dilation, is a result of the intense gravitational field of the black hole. As you approach the event horizon, the boundary beyond which nothing can escape the black hole's grasp, the effects of time dilation become even more pronounced. To an outside observer, it would seem as though you're frozen in time, hovering at the edge of the abyss. But, from your vantage point, everything continues as usual. The awe-inspiring view of the black hole, with its swirling accretion disk and the warping of space-time, would be a sight to behold. You'd be witnessing one of the universe's most enigmatic phenomena up close. The curvature of space-time around the black hole creates a gravitational lensing effect, bending light and distorting the view of the stars behind it. This cosmic spectacle is a direct consequence of Einstein's theory of general relativity. As you continue your descent, the gravitational forces grow stronger, but you remain unaware of the dramatic changes happening around you. The journey into a black hole is a journey into the unknown, a voyage that challenges our understanding of physics and the nature of reality. In this different view, the black hole isn't just a destructive force but a gateway to new realms of knowledge. It invites us to explore the boundaries of our universe and to ponder the mysteries that lie beyond. Section 8. The Black Hole Information Paradox. One of the biggest puzzles in physics is the black hole information paradox. This paradox challenges our understanding of the fundamental laws of physics, and has puzzled scientists for decades. At the heart of this mystery lies the question of what happens to information when it falls into a black hole. Quantum mechanics, the theory that governs the microscopic world, says that information can never be truly destroyed. This principle is known as the conservation of information. According to quantum mechanics, every particle and every bit of information about its state must be preserved, even if it undergoes a transformation. But what happens to the information about all the stuff that falls into a black hole? When an object crosses the event horizon, the point of no return, it seems to disappear from our universe. This leads to a troubling question. Does the information about that object vanish as well? Does it disappear forever, violating the laws of quantum mechanics? If information is lost in a black hole, it would mean that the fundamental principles of quantum mechanics are incorrect or incomplete. This has profound implications for our understanding of the universe. Or is it somehow preserved, perhaps encoded on the event horizon itself? Some theories suggest that the information is not lost, but rather stored on the surface of the event horizon in a two-dimensional form. This idea is known as the holographic principle, which proposes that the entire three-dimensional universe can be described by information encoded on a two-dimensional boundary. This paradox is still an active area of research and debate among physicists. Many leading scientists, including Stephen Hawking, have contributed to the discussion, proposing various solutions and theories. Despite significant progress, the black hole information paradox remains one of the most intriguing and unresolved questions in modern physics. Researchers continue to explore new ideas and conduct experiments in the hope of uncovering the true nature of black holes and the fate of information within them. Section 9. The universe's biggest mystery. Black holes are among the most fascinating and mysterious objects in the universe. They challenge our understanding of gravity, space, and time. While we've learned a lot about them, they still hold many secrets waiting to be unlocked. It's a reminder that the universe is full of wonders we're only beginning to grasp.